Hello class, this is Mr. Hart, and in this podcast we want to start the next part of our momentum unit, which is conservation of momentum. Okay. Now at this point we haven't done any conservation principles yet, but we're going to see a whole lot of these in physics. Okay. And what does that mean? What does it mean for something to be conserved? Okay, well let's just talk about it in terms of momentum, and it'll be pretty easy to see. Okay, so the conservation of momentum basically means that the initial momentum and final momentum are equal in a closed system. Okay? In other words, momentum initial equals momentum final mathematically. Okay? So in other words, if I took all the momentums in a system, okay, let's just say it's billiard balls hitting each other, for example. The momentum of the two billiard balls to start with has to equal the momentum of the two billiard balls to end with. Okay, momentum's a conserved property. Now, a key word here is it has to be a closed system, meaning it can't be experiencing some other outside forces. Okay, but as long as you're only working with a certain set of objects and only looking at their momentums and nothing else is interacting with them, then you're dealing with a closed system. Momentum will be conserved. Now, before we start looking at this mathematically, let's look at some of the types of collisions and how conservation of momentum is preserved in that case. Okay, so there's two basic types of collisions. There's elastic collisions, which just means they bounce off of each other, pretty simple, and inelastic collisions, meaning they kind of stick to each other, okay, like a football tackle, right? They move together with each other. So if you want an official definition, elastic collisions means the momentum is conserved, but the objects will stay separate or they'll bounce off of each other. And an inelastic collision means momentum is still conserved, but the objects merge together. All right, so we'll keep this in mind as we derive our equation. Okay, there's those two types of collisions. Okay, so let's derive the equation we're going to need to use. Okay, so if we start with the momentum initial equals the momentum final, and we write down that momentum is mass times velocity, okay, then mass times velocity initial equals mass times velocity final. Okay, then that means if we have, let's say, two objects, that's the only number we'll do in this class, is two objects colliding with each other, then the mass of the first object times the velocity of the first object plus the mass of the second object times the velocity of the second object initial, okay, equals the mass of the first object times the velocity of the first object plus the mass of the second object times the velocity of the second object final. Okay, that's a real tongue twister there. But point is, right, when these two objects collide, whatever their initial momentums each are, after they move apart, they still have to have the same momentum after you add their momentums, okay, after the collision. Okay? All right. Not quite there yet, because usually masses don't change in collisions. Okay? So we can just apply the initials to the velocity and the finals to the velocity. Okay, so when all is said and done, this is the full equation. Mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 times velocity 1 final plus mass 2 times velocity 2 final. Okay, that's a lot of stuff, okay, to keep in mind. And it's kind of hard to solve for these collisions because if it's just purely from this equation, usually you have two objects heading towards each other, and that's easy to find and measure. But you have two unknowns. You have the unknown velocity 1 final and the unknown velocity 2 final. Okay, so one equation, two unknowns, we can't solve that mathematically. Okay, now in like AP Physics, you'll learn how to use kinetic energy to get your second equation, but we're not going to do this in this class. Okay, so let's simplify a little bit. Okay, let's make it simpler. We're going to make an assumption here, and the assumption we're going to make, going back to collisions, is these are going to be inelastic collisions. Okay, meaning that they are going to stick together after they collide. So like a football tackle, okay, or catching a baseball in a glove or whatever it is, right? The objects stay together. Okay, this gives us a simplification because now the velocity 1 final has to equal the velocity 2 final because they're sticking together. Okay, so we're just going to replace velocity 1 final and velocity 2 with just v final. Okay, so now our equation becomes mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 velocity final and mass 2 velocity final. Hey, we got the same variable here. We can group those together, okay? So we're just going to say, hey, these both have velocity final, So we'll just call this mass 1 plus mass 2 times velocity final. Okay. If you distribute that out, it gives you the exact same result here. Okay. So we're assuming that they're inelastic collisions. So we get our final equation that we're going to use for this class. Okay. And that is this. So mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 plus mass 2 times velocity final. Okay? All right, a lot of work to get to that, but now we got a nice equation. We can use one unknown, the velocity final, and one equation. Okay? So the momentum is conserved. So after they hit into each other and they stick, they're going to have some final velocity. Okay? Using the conservation of momentum, we can find that. Okay? All right. Here's kind of just like a visual representation of what's happening. So they're heading towards each other. Okay, they hit, they strike, they stay together, and then they're going to have some final velocity together. Okay? We can find that using the equation we just had. Okay? All right. So let's try an example problem. Okay? So a baseball is thrown into a cart. Okay, so it's sitting on the floor. You just throw the baseball into the cart, trying to move the cart with the baseball. Okay, if the mass of the baseball is 0.145 kilograms and the cart has a mass of 5 kilograms, okay, and it's thrown at 20 meters per second and the cart was moving at negative 2 meters per second was the velocity after the collision. Okay. All right, a lot of information. Let's kind of visualize this really quickly. So we have a cart, little like wagon type thing. Sorry, that's the handle. Point is, okay, there's the cart. It's heading, let's call this direction negative 2 meters per second. And you throw the baseball this way, okay, at 20 meters per second. Lands in the cart, hits the cart back. What's its new speed? Okay. Now, it doesn't matter if you call negative left or right. Okay, the main thing is that you keep the negative consistent. So if this one's going negative 2 and that one's going 20, make sure you put that in the equation. Okay. All right. So mass 1, let's call mass 1 the baseball. So mass 1 is 0.145 kilograms. The velocity 1 of the baseball is 20 meters per second. Mass 2 is 5 kilograms. Velocity 2 is negative 2 meters per second. Okay. All right, let's see if I can fit that whole long equation on this page. So we got mass 1, velocity 1 plus mass 2, velocity 2 equals mass 1 plus mass 2 times velocity final. So we need to solve for this and move these guys down here. So I'm going to take them off from here. And we have V final equals all this over mass 1 plus mass 2. So I just moved mass 1 and mass 2 from this side down to here. All right, I'm not going to take the time to rewrite all these, but mass 1's this, V1's that, M2's that, V2's this. So we're just going to plug those all in. Okay, put those into our calculator. So 0.145 times 20 plus 5 times negative 2 over 0.145 plus 5. Okay. All right, so if you do that all correctly, you should get that V final is negative 1.38 meters per second. Okay, so even though you threw the baseball in there, it just slows it down. It doesn't even stop the cart because this is still negative. Okay, but there we go. So that is V final. That's the final velocity of that system. Let's try one more problem. Just make sure we got this down. Okay, so an 80 kilogram cop is chasing a 73 kilogram criminal down the street. If the cop is running at 5 meters per second and the criminal is running at 4 meters per second, what is their velocity after the cop tackles the criminal? Okay, so just make sure, always check the velocities in this case. This type of collision, they're both heading in the same direction. Okay, so we'll make both of them positive, okay, which it has written here. But just always check. If they're hitting into each other like this, it should have one be positive, one be negative. If they're hitting into each other like this, which in this case we do have because there's a cop chasing one guy, they're heading in the same direction, then they both are positive. Okay, so let's just identify. So we got mass 1 equals 80 kilograms. Make the cop mass 1, mass 2 is 73 kilograms. Velocity 1 is 5 meters per second, and velocity 2 is 4 meters per second. Okay, so then what we say is, all right, our equation is mass 1 times velocity 1 plus mass 2 times velocity 2 equals mass 1 plus mass 2 over V final. Okay, and again in this case we're solving for V final, so we can just divide by mass 1 and mass 2 and put it onto the other side of the equation. Okay, so we're going to put this down here, mass 1 plus mass 2, and so we get that V final is that. Okay, and again, I'm not going to take the time to write this all out, but we'll plug in 80 for mass 1, 73 for mass 2, and so on. Okay, so if you put that in your calculator, 80 times 5 plus 73 times 4 divided by 80 plus 73 gives us that the final velocity is 4.5 meters per second. Okay, cool. So there you go. So after he tackles them, they're going to be both moving at 4.5 meters per second. And this points out an interesting part of this equation, something that comes from the conservation of momentum. If you have two objects that are traveling in the same direction and they collide into each other, the speed that the collision is going to be going, or the speed after collision, I should say, is going to be between their two velocities. Okay. So in this case, the cop is going 5, the criminal is going 4. Okay. So their final velocity was between those two values, 4.5. Okay. Now it's not always going to be half, but it will be between 4 and 5. Okay. And that's for any collision where the two objects are moving in the same direction. The final velocity is between their two original velocities. Let's look at some interesting applications that come from the conservation of momentum. One that I often think about is gun recoil. Okay, I have a friend that likes to go shooting a lot, and one time I went up with him and he let me shoot his 9mm pistol, and I'll tell you, that thing has a lot of kick. You gotta make sure you're holding that gun right. Okay, but as soon as that ball goes out, your hand shoots back from the gun. Okay, or a shotgun. I shot one of those once, and man, those things have some recoil. Okay, but let's think about why. Okay, it's a conservation of momentum. Okay, so if you have the gun and the bullet just sitting there to start with, okay, their initial momentum is 0, right? So the momentum initial is 0 if the gun just has the bullet sitting there. Nothing's moving. It's just 0. Okay, well, all of a sudden, you shoot out the bullet with the gunpowder or whatever it is, right? And the bullet goes flying this direction. Okay, it has a certain momentum. Okay, in that direction. Well, if momentum's conserved and you started with 0 momentum, okay, the gun just can't sit there. It has to also have some momentum that goes with it. Okay, so its final momentum is going to go that way, right? So these two momentums have to be the same because to start with, you didn't have any momentum. You had an initial momentum of 0. Okay, and that's why your gun recoils, because believe it or not, that bullet has a very high momentum. Even though its mass is pretty small, okay, it has a huge velocity. Okay, and so that's what gives it so much momentum. So likewise, your gun has a pretty big mass compared to it, so it'll have some velocity to it, okay, which is what you feel as the recoil. Okay, but that comes from conservation of momentum. Okay, another cool example of this is the idea of propulsion for rockets. Okay, a lot of people think, oh, the rocket fuel is pushing off the ground, and that's why the rocket flies. No, it has nothing to do with that. Right? How else would the rocket be going in space? There's no way that fuel is going all the way to the ground to hit the surface. It has to do with momentum, right? Because if you just have the rocket sitting there, okay, then its initial momentum is just 0. Okay, rocket with the fuel sitting there ready to launch has a momentum of 0. Okay, now all of a sudden you start to shoot off the rocket fuel towards the ground, right? It doesn't have to hit the ground, it just has to go in that direction. It has a final momentum in that direction. Okay, Well, what does the rocket have to do in return? It has to have a momentum in the other direction. Okay. Now, rockets are pretty big, so you have to have quite a bit amount of fuel to get that going, but it's conservation momentum. You started with nothing, no momentum, so if you suddenly shoot the fuel out the bottom, guess what? The rocket has to go up to conserve momentum. Okay. Now, there's a lot of ways you can describe rocket launches. You can think about Newton's third law and other things like that, but one way to think about it is conservation of momentum. Okay. Alrighty, but that's the math and the applications, and it's a pretty cool principle. Kind of a long equation, but it's very useful. Just make sure you do the homework, the conservation of momentum homework. But that's it. Let me know if you have any questions, and thank you for watching.